Hello again. We are going to move forward in our discussion of recurrence relations. We just finished talking about first order recurrence relations, and now we're going to talk about second order recurrence relations. And if you could guess what that means, it means that every term in a sequence is defined by the first and second term that come immediately before it. So whenever we talk about un, it's going to be defined in terms of un minus 1 and un minus 2, or something very, very close to that. So let's begin. The most popular example of this is the Fibonacci sequence. That's the one that starts with 1 and 1, and every term after that is the sum of the two terms that come before it. All right, so u1 is 1, u2 is 1, and un plus 2 is equal to the sum of the n plus first term and the nth term, so the two terms that come before it. So it goes 1, 1, 2, 3, 5, 8, and 13, and obviously you can keep going. Okay, so the goal is the same as it was for first order recurrence relations. We are trying to write this in terms of n only. All right, so here's our strategy. That's how it's going to be given to us. The n plus second term is going to be equal to some constant times the n plus first term, or the term that came before it, plus another constant times the term that is 2 before that, which we will call un, or the nth term. So here's what we're going to do. We're going to create an equation that is k squared plus ak plus b. So my k's are variables for now that need to be solved for, but my a and b are going to come directly from that equation that I was given. So the a is going to be the coefficient of the n plus first term, and the b is going to be the coefficient of the nth term, and I'm going to go from there. So the general solution for the nth term is going to be some constant 1 times your first solution to the n, plus another constant that I'm going to call C2 times your second solution raised to the n. Again, it's a little confusing now until we go through some examples, but we will definitely do that. So we're going to apply the general solution to u1 and u2, and we're going to get values of those constants, C1 and C2. All right, and we're going to write the solution. Now that we know what C1 is, K1, C2, and K2, we will have all of that stuff by step 4, so we will be able to write our solution to that second order recurrence relation. Okay, if they are complex, if those solutions that we found in step 1 are complex, we may have to write the solution in polar form, and again, I will give you an example of how to do that. All right, so that's our general strategy. Let's start with an example. We have that the n plus second term is equal to 5 times the n plus first term minus 6 times the nth term, where the first term is 5 and the second term is 13. All right, so my a, which is the coefficient of the n plus first term, that's 5. And my b, that's the coefficient of the nth term, that's negative 6. So my auxiliary equation is k squared equals 5k minus 6. So I need to solve that, and since it's a quadratic, I like to solve quadratics by moving everything to the left or to one side so that there is a 0 on the other side. So this is the quadratic I have to solve. K squared minus 5k plus 6 is 0. That can actually be factored into k minus 2 times k minus 3 equals 0. So that means that my first constant is 2, my second constant is 3. It doesn't really matter. Those could easily be switched so that k1 was 3 and k2 was 2, and it doesn't really matter based on how the final solution looks. So there's my general solution. There is some constant being multiplied by 2 to the n, and then to that we are going to add a second constant times 3 to the n. Okay, so now I just need to figure out what those two constants are. So I know what the first term is and what the second term is, so let me use that information. The first term is that unknown constant times 2 to the 1 plus the second unknown constant times 3 to the 1, and that's supposed to equal 5. Well, if I rearrange that to look a little nicer, then I get 2c1 plus 3c2 equals 5. Applying the same thing to the second term, so the unknown constant times 2 squared plus the other unknown constant times 3 squared, that has to equal 13. And if I rearrange that to look nicer, then it is 4c1 plus 9c2 equals 13. Well, over here, this is a system of equations that I can solve using technology or by hand. It really doesn't matter. But if I solve this, it's kind of a nice solution that the first constant is 1 and the second constant is also 1. So the general solution was that the nth term was some unknown constant times 2 to the n plus another unknown constant times 3 to the n. And what I found was constant 1 is equal to 1 and constant 2 is equal to 1. So I can make those replacements. So my general solution is that the nth term is 2 to the n plus 3 to the n. So that's a simple example where I don't need to use polar form. But now let's do one that has complex k values. Okay, so totally different example. We have the relation that the n plus second term is equal to twice the n plus first term minus 2 times the nth term. The first term is negative 6. The second term is negative 12. Okay, so using those constants that are in the original relation, I need to find the solutions k1 and k2 to the auxiliary equation k squared equals 2k minus 2. And hopefully you can see where I got that 2 and that negative 2 from. That came from the original relation. So again, it's a quadratic, so I move everything to one side, and hopefully I can factor it. K squared minus 2k plus 2 equals 0. I can't really factor that. So I have to use the quadratic formula, and that gives me that the first constant is 1 plus I, the second constant is 1 minus I. Again, those are interchangeable. K1 and K2 can be either or based on what the general solution looks like. And we've seen that in the last example. So my general solution is that the nth term is some unknown constant times 1 plus I to the n plus another unknown constant times 1 minus I to the n. All right, so that's what it looks like. I just have to figure out what the first constant and second constant actually are. So I'm going to apply this to the first term, and what I get is my unknown constant times 1 plus I to the 1 plus my second constant times 1 minus I to the 1 has to equal 5. And if I write it nicely and distribute everything, I get what you see on the right. Constant 1 plus constant 1 times I plus constant 2 minus constant 2 times I equals negative 6. And if I group them so that the real stuff is together and the complex stuff is together, I get this equation right here. So the real stuff is C1 plus C2. The imaginary stuff is C1 minus C2 times I, and all of that has to equal negative 6. Or C1 plus C2 has to equal negative 6. And the reason that I did that is because if you look at the number on the right, it's negative 6. That's a real number, and there is no imaginary part to that. So I know that if I subtract the C1 minus C2 in order to figure out this coefficient of I, then I will get 0. So C1 minus C2 is 0. I really only need to do that. I really don't need to look at the second term. So I know that C1 is negative 3 and C2 is negative 3. And so now I can write my solution as negative 3 times I plus 1 to the n minus 3 times I minus 1 to the n. Okay. But if they were looking for polar coordinates, which is sometimes what you need to do with complex numbers, then I need to convert each individual part of it to polar. So 1 plus I, if you remember your polar form from last year, 1 plus I converts to the square root of 2 times cis pi over 4. And I use cis, it's a short form for cosine of pi over 4 plus I times the sine of pi over 4. So get used to that short form. It's also in textbooks and everything, so make sure you know what that means. It's totally acceptable for you to use that short form. It's not something I made up. And similarly, 1 minus I converts to the square root of 2 times cis negative pi over 4. All right, so I can write the nth term is negative 3 times root 2 times cis pi over 4 to the n minus 3 times the square root of 2 cis negative pi over 4 to the n. Okay, now you need to remember de Moivre's theorem as well so that we can apply this n exponent. Okay, and if you remember, what happens is the magnitude or the r value here gets raised to the n, and then the angle gets multiplied by that n in each case. So my nth term is negative 3 times 2 to the n over 2 cis n pi over 4 minus 3 times 2 to the n over 2 cis negative n pi over 4. So that's where we are right now. It's still a little messy, so we do need to clean that up. That's where I left off, so nothing is new there. But you need to remember that the cis of something means the cosine of that angle plus I times the sine of that angle. That's actually what it's short for, as I mentioned earlier. So I'm actually going to spread that out and write it using its actual definition. And there's a reason for that, that you'll see in a minute. So all I've done is I've changed cis of that angle to cosine of that angle plus I times the sine of that angle in both cases. So the angle in the first set of parentheses was n pi over 4, and the angle in the second set was negative n pi over 4. But other than that, everything is the same. So then things get even messier because now I have to multiply this negative 3 times 2 to the n over 2 by each of the two things that are in each set of parentheses. So try and follow where these four terms came from. The first two came from this expansion, and the last two came from this expansion. Now I need to remember a couple of rules about trigonometry, and that is that the cosine of negative x is the same as cosine of x. And the sine of negative x is equal to the negative sine of x. Those are properties of trigonometry that you hopefully discussed a lot earlier than this. And that actually comes in helpful because I have the cosine of a negative angle and the sine of the same negative angle as the third and fourth terms here. So I need to make some adjustments to that so that the angles in the third and fourth terms match up exactly to the angles in the first and second terms. And that's what I get. Notice that in moving from cosine negative n pi over 4, I can simply say that it is the same as the cosine of positive n pi over 4. And over here, I can't just simply drop the negative because the sine of negative x is not equal to the sine of x. I can drop that negative as long as I put a negative out in front of it. So now I have some like terms. The second and the fourth terms, if you notice, they are exactly the same, but there's a negative in front of the fourth term. And so all I have left is the first term and the third term. And they look exactly the same, and they are being added together, so there are two of them. So I have 2 times the first term, or you can think of it as 2 times this term right here, whichever one you want to think of it. But that 2 sitting out front is being multiplied by these n over 2 2's that are sitting just a couple steps away. So everything's being multiplied together. So I actually have 2 to the 1 times 2 to the n plus 2. And if I add those together, I get 2 to the n plus 2 over 2. That gets multiplied by negative 3. That gets multiplied by the cosine of n pi over 4. So that's an example of using polar coordinates. And you have to remember a lot from last year in order to be able to do that. All right, now there is a special case. What if, when we are finding the solutions to the auxiliary equation, what if the solutions are the same? In other words, K1 and K2 are actually equal to each other. Well, we follow these steps instead. I'm going to say that the nth term is C plus dn times K to the n. Okay, and we apply the general solution to U1 and U2 to get the values of C and D. And I write my answer like that, replacing C and D and that repeated value of K as my solution to the auxiliary equation. So obviously we need an example of this. So we have the n plus second term is equal to 4 times the n plus first term minus 4 times the nth term. And I have the first term is 5, the second term is 12. So if I solve that auxiliary equation, it is k squared equals 4k minus 4. I move everything to the left and I get k squared minus 4k plus 4 equals 0, and that has a repeated root of k equals 2. So what I'm going to do is I'm going to say that the nth term is c plus dn times 2 to the n. Apply that to the general solution. So the first term, 5, is equal to c plus 1 times d times 2 to the 1. And u2, the second term, which was 12, that's equal to c plus 2d times 2 to the 2. I can rearrange that to get this system right here. 2c plus 2d equals 5, and 4c plus 8d equals 12. So the solution is c equals 2 and d equals 0.5. And so I can write the answer as the nth term equals 2 plus 0.5n times 2 to the n. And that's how you would do it if the auxiliary equation gave you repeated roots. That's the only time you would use this special way. As you can see, it's a lot quicker. But that's about it for this. There's one more lesson after this, and that is about modeling. But if you have any questions about this, please let me know, and I will see you tomorrow.